Hi everyone, this is part 1 of the lecture to accompany chapter 10 in your textbook. Please read chapter 10, there's lots of information I don't have time to address. Okay, let's get started on truth-functional logic. Despite the power and rigor of categorical logic, which we learned about in chapter 9, its methods really only apply to syllogisms in which each of the two premises can be translated into a standard form categorical claim. It doesn't work to evaluate the validity of other types of deductive argument structures. Truth-functional or propositional logic is another way to determine validity, and it deals with the logic of sentences. This chapter shows how to work with complex arrangements of individual sentences. You're going to use letters to represent whole claims and a few special symbols to represent the standard relations among those claims. Roughly speaking, the relations that correspond to the English words not, and, or, and if-then. Truth tables and rules of proof show how the truth values of the individual claims determine the truth values of their compounds and whether or not a given conclusion follows from a given set of premises. Those of you who have taken courses in math and computer programming might already be familiar with this kind of logic. It has applications as wide-ranging as set theory and fundamental principles of computer science, as well as being very useful for the examination of ordinary arguments. This is a very, very basic discussion of propositional logic, and only as it applies to how we would use it to determine the validity of an argument. One of the major ways that we determine validity in propositional arguments is by using something called a truth table. Like the Venn diagrams in Chapter 9, they help you to see whether the premises guarantee the truth of the conclusion. They look complicated and difficult, but frankly, they're pretty simple. All you're doing is visually representing all the possible combinations of the truth values of each claim and the conclusion. We won't get into long, complicated arguments here, as I just want you to understand how they work. But we're going to look at several examples and do one or two in class to make sure that you understand the concept. Unlike categorical claims, where you use letters, also known as variables, to represent individual terms within each claim, in propositional claims you use variables to represent entire claims. And each claim variable has a truth value. In other words, the claim itself is either true, which we represent with T, or false, which we represent with F. Now, in order to use truth tables, you have to understand the 4 different types of claims that you'll be using. The first type is negation. Any given claim has a truth value, which means that its contradictory claim, called a negation, will have the opposite truth value. So if you know for sure that a particular claim is true, you know the opposite of that claim is false. A conjunction is made up of 2 simpler claims, and the only time it can be considered true is if both of those claims are true. If either or both of them can be proven false, then the entire statement is false. A disjunction is also made up of 2 simpler claims, except that if either of the claims is false, the statement will still be true. The only time it's false is if both of the claims it makes are false. Finally, conditional claims are also made from 2 simpler claims, but in these ones they state that if the first claim is true, then the second claim must also be true. So now we're going to look at examples of each of these types of claims to make it clearer for you. Okay, this is what negation looks like. If P is true, then not P is false. And if P is false, then not P is true. To show the not part, you use the squiggly negation sign that's generally up on the left side of your keyboard by the numbers. So if you were to make a truth table out of this, it would look like this. You would write P and not P at the header of those 2 columns, and then on the next lines, the potential truth values. So on the first truth values line, you would put T under the P and F under the not P. And on the next line, the next potential truth value is false, which makes not P true. So let's say that P represents the claim Percy is 6 feet tall, and you have determined that this is true. Then not P would represent the claim Percy is not 6 feet tall, and its truth value would be false. However, if you determine that Percy is 5'9" tall, then that would make the truth value of P false, and not P would be true. A conjunction is made up of two smaller claims, usually linked together with the word and represented by an ampersand. A truth table for a conjunction has to show all the possible combinations of truth values of its claims. Remember, in order for a conjunction to be true, both of its smaller claims must be true. If either or both of them is false, the entire conjunction is false. Because you're dealing with all the possible truth values of the combination of both the claims, there are more lines on this truth table than the last one. You need 4 lines to show all the possible combinations of true and false. So the first line, both P and Q are true, which makes the conjunction true. The second line, P is true and Q is false, which makes the conjunction false. The third line, P is false and Q is true, makes the conjunction false. And the fourth line, P is false and Q is false, also makes the conjunction false. The example here uses this truth table. Percy is at home and so is Quincy. So the only way this entire statement is true if it can be determined that both Percy and Quincy are at home. If either one or both of them are not at home, then the entire claim is false. A disjunction is also a combination of two smaller claims. However, in this type of claim, the terms either and or are used to designate that one or both of the smaller claims is the case and is represented by a V or a wedge shape. Unlike a conjunction, though, these claims are only false if both smaller claims are shown to be false. So in the example, either Percy's at home or Quincy is, it's still true if both or either of them are at home. It's only false if you can show that neither of them are at home. Finally, conditional claims. These are made of two smaller claims that say if the first claim is true, then the other one must also be the case. The if-then is represented by a right-facing arrow and pronounced as if P, then Q. In conditional claims, the only time the entire claim is considered false is if the antecedent, the first claim, is true, but the consequent, the second claim, is false. Now, some might argue that the third line, P is false but Q is true, should also be false, and some philosophers would agree. However, for purposes of what we're doing here, we're going to go with what's called the material conditional, which says that conditionals are always true unless the antecedent is true but the consequent is false. So the example, if Percy is at home, then Quincy is at home, is still true, even if you can show that Percy isn't home but Quincy is. It's only false if you can show that Quincy isn't there. Yeah, it's a little confusing, but just something you have to know. Okay, before we create a couple of truth tables, we need to familiarize ourselves with some important rules. The first is that you should use parentheses as necessary to group things together, as in this example. If Paula goes to work, then Quincy and Roger will get a day off. Is symbolized as if P, then the combination of Q and R. This is a conditional claim, but it also has a conjunction in the consequent part of the claim. So you would put parentheses around the Q and R part to symbolize this. The second rule is that you have to capture all possible combinations of truth values for individual parts of a complex claim. And the third rule is that you have to have columns for each part of the claim. So for the above conditional claim, you'd need 5 columns. You'd need one each for P, Q, and R, one for the combination of Q and R, and one for the entire claim. You'd also need 8 lines to capture all the possible truth combinations. And if you want to see what the truth table for this claim looks like, it's on page 290 in your textbook. So let's create a truth table. Here's the argument. If building the bookshelf requires a screwdriver, then I will not be able to build it. After reading the directions, I can see that a screwdriver is needed, so I can't build it. We will label needing a screwdriver as S and building a bookshelf as B. Then we need to translate the argument into standard form. We can then read it as if S, then not B. S, therefore not B. And you can see the symbolized argument at the bottom of the page. So now we need to organize our truth table. We've got 2 premises. If S, then not B is the first premise. S is the second premise, and the conclusion is not B. But if we look at the first premise, we have the other premise and the conclusion in it already. So if we make the table with the antecedent S, the consequent not B, and the conditional premise, we'll have everything we need. Then we just need to fill in the table. So if S and not B are both true, then the premise is true. If S is true and not B is false, the premise is false. If S is false and not B is true, the premise is still true, and if both S and not B are false, it's still true. So now we put the argument in the correct order. An argument is valid if it's impossible for all the premises to be true and the conclusion to be false. And if we look at this table, we can see that there is not a row in which all the premises are true, but the conclusion is false. So we know that this argument is valid. Let's do another one. Martin is not buying a new car since he said he would buy a new car or take a Hawaiian vacation, and I just heard him talking about his trip to Maui. We have to first translate that into a form we can work with. It looks like the conclusion of this argument is that Martin is not buying a new car. And the reasons are that he said he would either buy a new car or take a trip to Hawaii. That's the first premise, and it's a disjunctive claim, either or. And he was talking about his trip to Maui, which is the second premise. So we can label buying a car as C, going to Hawaii as H. So this argument can be translated to either C or H. H, therefore not C. And you can see the symbolized argument at the bottom. So now we need to create the table with columns for the claims and fill it in based on the rule of disjunction, which, if you remember, says that the only time a disjunctive claim is false is if both of its smaller claims are false. So the first line is true, true, and true. The second line is true, false, true. The third line is false, true, and true. And the fourth line is false, false, and false. Okay, we already have the truth values for the second premise, which is H, as part of the disjunctive claim, so to do it again would be redundant. But we need to add the column with the conclusion, which is not C, and to determine its truth values. So in the first line, if C is true, then not C is false, and so on down each line. So the second line, not C is false. The third line, not C is true. And the fourth line, not C is true. Now that you've completed the table, you need to look at it to see if any row shows all true premises but a false conclusion. And yes, the first row has all true premises and a false conclusion. And a valid argument can't have that. So this argument is invalid. Now, it might seem like this would have been a valid argument, but it's not, because its structure, the form that it's in, is incorrect. Later in part 2 of this lecture, I'll show you different valid and invalid argument structures, and it's going to make more sense to you. Sometimes conditional claims can be a little confusing, so you need to look at the wording carefully to make sure you're interpreting it correctly. 3 words or phrases using the word if can be problematic, but if you learn the rules for them, it can make it easier. First, the word if by itself. When it's used alone, it signals the antecedent, which is the first claim of a conditional claim. If the boat capsizes, I will get wet. If the boat capsizes is the antecedent, I could say it as I will get wet if the boat capsizes, and if the boat capsizes is still the antecedent, and these are both symbolized as if B, then W. Only if introduces the consequent of a conditional claim. I will get wet only if the boat capsizes. And that can be rephrased as, if I get wet, then the boat will have capsized. And these are both symbolized, if W, then B. And finally, if and only if turns the smaller claims into both antecedent and consequence, because you need both of them to work together. I will get wet if and only if the boat capsizes. And this is symbolized as if W, then B, in parentheses, and if B, then W. Conditional claims are sometimes spelled out in terms of necessary and sufficient conditions. A necessary condition is something that you absolutely must have for something else to be true. So a necessary condition is a consequent of a conditional claim. This example shows how it works. The presence of oxygen is a necessary condition for combustion. And that means we can't have combustion without oxygen. So it needs to be if C, then O. If there's combustion, then there must first be oxygen. Sufficient is different. Sufficient means enough, as in that's all you need. So it expresses the antecedent of a conditional claim, as in this example. Being born in the United States is all you need to be a U.S. citizen. So if B, then C. If you're born in the United States, then you're a citizen. This is the end of part 1. Please move on to part 2.